Good day, grade 12, and welcome in our third video in our series on work, energy, and power. In the previous video, we touched on objects on an incline. We did two examples, one with friction, one without friction, but then I gave you an example to do at home of an object on a frictionless surface. We'll quickly mark that one, and then we'll continue and look again at another example on an object where we have an applied force as well as friction force acting on an object and to calculate the amount of work done. But before we do that, let's quickly mark the problem that was given in the previous video. If you haven't done that problem yet, it is vital that you stop this video now and first do it. Remember, science is not a spectator sport. You need to develop cognitive functions, and you do that by struggling with problems, by getting them wrong, by checking the answer, by redoing it, by figuring out what you did wrong. You cannot do any of that by just sitting and watching a video. That is why we have so many videos, so that each of them end in a problem which you can do on your own. So let's quickly tackle this one. A block with mass 5 kg is sliding on a frictionless surface as indicated below. The surface makes an incline of 25 degrees with the horizontal. Sorry for that spelling error. Calculate the work done by the gravitational force acting on the block while it covers the distance of 3 meters. We have gravitational force acting on this block, and we need to calculate the amount of work done. For that we use our formula W equals F, which is the force, which in this case will be the gravitational force, delta x, which is the distance that this block is covering, cos of the angle between the force and the direction that this thing is moving. But we don't have that angle, do we? We only have the angle that is between the horizontal and the incline, and this angle is not equal to the angle between the direction of motion and the gravitational force. So we first have to determine that angle. For that, we're going to use a little bit of maths. Okay, we need to find this angle. The direction in which this block is moving is parallel to the incline. And we know the angle between the incline and the horizontal is 25 degrees. We also know the horizontal and the vertical is 90 degrees on top of each other, by definition of horizontal and vertical. And we know the gravitational force is going vertically down. We also know in a triangle, the three angles of a triangle must always give 180 degrees. So therefore we know the sum of these three angles, because they form a triangle, need to be 180 degrees. So in order to get the angle between the gravitational force and the direction that this object is moving, which is this angle here, I can use trigonometry and say 180 minus 90 is 90 degrees, minus 25 will give me 65 degrees, which is that angle. So now I can go and plug in all these values in my formula. The gravitational force is mass times gravitational acceleration, times the distance that this object is moving is 3 meters, cos of the angle between the direction that he is moving and the force. And if I calculate that, it will give me 62.12 joules. Number 2, calculate the work done by the normal force acting on the block. The normal force makes an angle of 90 degrees with the direction in which this block moves. So even though I don't have the size of the normal force, I know that cos of 90 is going to give me 0. So although I don't have this number, anything times 0 is going to give me 0. So I know the resultant force acting on this block is going to be 0 joules. Calculate the work done by the friction force. This was not a nice question. To be honest, I think I had something else in mind when I initially started this worksheet. I think I kind of forgot about this little word when I put in this question. This is a frictionless surface, so there is no friction force. Therefore, if I add in the values for friction is 0, so 0 times 3 cos 180 it's going to give me 0 joules, because this value is 0. 0 times anything is 0. Bit of a silly question, sorry for that. 2.4, calculate the net work done on the block. So that I can calculate on one of two ways. I can either calculate the work done by each force separately and then add all those two values together to get the total work done. Or I can go and calculate the resultant force acting on the block. And once I've got the resultant force, I can put it into this equation. I'm going to show you both ways and show you that in each of these cases we'll get the same answer. Depending on the situation in your question paper, sometimes it's easier to use this method, other times it's easier to use that one. Okay, so let's see. Let's start with calculating the work done by each of the individual forces, because we have done actually this in the previous first 3 questions, or in the first 3 parts of this question. The work done by the friction force, actually there's no friction force acting, so we calculated that as 0. I just added there since there was this ridiculous question 2.3. We calculate the amount of work done by friction force as 62.12 joule. And we know that the work done by the normal force is equal to 0. So this becomes a very easy sum where we just have 0 plus 62.12 plus 0, which gives me 62.12 joule. Or I can from the beginning work out the resultant force acting on the object and then calculate the work done. Let's see how that's done. There's the force acting on my object, my normal force and my gravitational force. So what I'm going to do is I'm going to break up my gravitational force into 2 components. One that is parallel to the slope, that's that one, and one that is perpendicular to the slope, this one. Why would I want to do that? Because I know the forces that's parallel or perpendicular to the slope are going to add up to 0. How do I know that? Because this object is only moving in this direction, so parallel, the perpendicular to this direction must add up, must give me a force of 0. Okay, so let's look at our normal force, or the forces perpendicular to the surface is our normal force, plus this component, which is equal to mg cos of 25, so those two must equal up to 0. If we look at the parallel forces, the only force acting parallel on this slope is the component of the gravitational force, which is mg sine theta, and that's going to be my resultant force. If I calculate that, m mass is 5, gravitational acceleration is 9.8, sine of 25. If I calculate that on my calculator, I get a resultant force of 20.71 Newton. If I put this value or substitute this value into my equation, then I get the work done is 20.71 times 3, which is the distance that this one is moving, or delta x, cos of the angle between the direction that this thing is moving and the force. And the force, the parallel component, this force is also acting in this direction, so the angle between these two are 0. A number of learners just put in, if they see theta, they look for a theta on any theta on a sketch. So often we see that a learner would typically put in here the value of 25. Make sure that you understand these values. Theta is the angle between the direction that this thing is moving and the force that you are calculating at the moment. We are calculating this component of the gravitational force, which is parallel to the direction in which the object is moving. That means the angle between those two are 0, and that is why I use the 0 over here. Can you see the answer that I get here is exactly the same as the answer in the previous calculation? Oh, let me just wait for the black bar to disappear again so that you can see. There we go. In the calculation where I added up the amount of work done by each of the forces, I got 62.12 joule. And here where I calculated the resultant force, I also get 62.12 joule. So you can see that they will give you exactly the same answer. Let's have a look at another example. A block with a mass of 4 kg on an incline of 15 degrees is pulled with a force of 20 Newton over a distance of 1.5. A friction force of 2 newtons act on the block. Calculate the work done on the block. Now that I read this question, I realize it's stated a little bit ambiguously. You don't know whether the 20 Newton force is going down or whether it's going up. I did not specify that. So I'm just going to tell you now. Let's assume that it's going up for the sake of doing this sum. Okay. Now we can calculate the amount of work done on one of two ways. We can either calculate the work done by each individual force that is acting on the block, or we can first go and see what the calculate the resultant force acting on the block, and then calculate the amount of work done by the resultant force. And again, as in the previous case, I'm going to show you how both of these examples are done. So let's start with calculating the individual forces acting on the block. And before we do that, we need, that's right, a free body diagram. So what are the forces acting? We've got the normal force, we've got a friction force. Remember, I told you I'm going to assume that the 20 Newton is going upwards. So my friction force of 2 Newton is going parallel to the block but downwards. Gravitational force is always towards the earth, and then my applied force of 20 Newton is going up the incline. I made all of these forces different colors. I'm going to do the calculation in the same color as the forces so that you can easily follow which calculation belongs to which force. So let's start with the work done by the normal force. Now by now you know already the normal force is 90 degrees on your direction of motion. So therefore cos of your angle, which is the angle between the force and the direction of motion, is going to be 90. Cos of 90 is 0. So I know that my normal force is not going to have an influence on the calculation of the work done. So let's look at the next force, which is the friction force. Okay, the friction force I know is 2 Newton. It's acting over a direction, a distance of 1.5 meter. This thing is moving 1.5 meters upwards. Friction force is working in this direction. The angle between the direction in which this force is acting, the friction force is acting, and the direction in which the block is moving is 180 degrees. Remember, I do not put in the for the force, because it's an opposite direction, I do not put in a negative sign here. I only use the magnitude of the forces. There, this will sort out. This cos of 180 will call, or the size of the angle will sort out whether this work done is going to be positive or negative. And indeed, cos of 180 is minus 1. So 2 times 1.5 times minus 1 is equal to minus 3 joule. So therefore I know my friction force is negative 3 joule. So I calculated my normal force, my friction force, and let's go with the applied force. That's also a nice and easy one. Applied force is 20 Newton. It's moving over a distance of 1.5 meters, and the applied force and the distance over which this object is moving is exactly in the same direction. So the angle between those two is 0. So I just have 20 times 1.5 because cos of 0 is 1, and that will give me 30 joules. So I calculated the normal force, the friction force, the applied force. Now let's have a look at the gravitational force. Now for the gravitational force, I need, remember, to fill in this equation. I need the distance over which it's moving, the force itself, which is mg, mass times gravitation, times the 1.5. But this theta is the angle between the gravitational force and the force that not the gravitational force, not the angle between the force and the gravity, and the direction in which this object is moving. Now the direction in which this object is moving is exactly the same as this applied force. Therefore I indicated this angle over here. I need the size of this angle over here. Okay, it's not that I need the angle between these two forces. No. I need the angle between this force and the direction in which this object is traveling, but the direction in which the object is traveling happens to be the same as the direction of this force. So how do I get that angle? You can't just put in 15 there because it's the only angle that's on the sketch. That is not the angle that is used to this calculation. So how do I use this 15 Newton that I have? Well, I know the angle between the horizontal and the incline is 15. I know this one is 15. So if I put a horizontal there, then I will know that this small angle over here is going to be 15. I also know that the angle between the horizontal and the vertical is 90 degrees. So if I simply add up these two, I get 90 plus 15, which is 105, and then I calculated this angle. Can you see how important it is that you are able to do your mathematics? Because at times we seamlessly just apply the mathematics that you did earlier. Okay, so now that we know that this angle is 105, I can plug in all the different values, and I get my work done by my gravitational force as negative 15.22, which makes sense because the angle between the force and the direction of motion is more than 90 degrees, so I know I will get a negative work done. So in order to calculate the total work done, I just need to add up the values for each, the work done by each of these different forces. And if I do that, I get an answer of 11.78 joule. So now let's go into do the same calculation, or solve the same problem rather, but with a different calculation. So now we are first going to calculate the resultant force, and then work out the work done by the resultant force. So there's my force diagram, but now what I've done, I just resolved my gravitational force into its two components, the perpendicular as well as the parallel component, parallel to the incline and perpendicular to the incline. Remember, you have done this in grade 11 to calculate these two components. Okay, so what do we know about the forces that are parallel to the plane? Well, these two forces will cancel out, or if I add them up, they will give me a resultant of 0. And then the sum of the forces on the incline, that will give me my resultant force. Remember, I told you work done is a scalar. So we don't bother with directions as when it gets to work done. But when we calculate forces, and this is what we're doing now, we're calculating a resultant force, then we are dealing with vectors. And always when you deal with vectors, you have to choose a direction as positive so that you have the opposite direction as negative. So I'm going to decide going up the incline is positive. And then I'm going to add all the forces in this plane. How many are there? 1, which is the 20 Newton. 2, which is the friction force, and 3, which is the parallel component of the gravitational force. 20 Newton is acting in this direction, which I chose as positive, so that will be a positive number, whereas the other 2 are both negative forces. So let's plug in some values. Remember, the component that is parallel to the incline, I can calculate that using mg sine theta. If you don't know why this force is mg sine theta, it might be a good idea to revisit your grade 11 work breaking up into components. If you really don't know where to find that, contact your teacher or contact me and I will try to sort you out on that one. Okay, so now we know that our resultant force is 20 minus mg sine theta, where theta is just the angle between the ground and the incline, minus my friction force. So I put in all my different values. I know my friction force is 2 newtons, and if I calculate this, I find my my resultant force is 7.85 newton. But this is not what I wanted to calculate. I wanted to calculate the total amount of work done. So for that I use my work equation. Once I substitute all the values into my work equation, I get my final answer exactly as I did in the previous sum, as 11.78 joules. Now, I've referred before to positive and negative work, but let's just quickly summarize what that actually means. I do positive work when the interior angle between the force applied and the direction of movement is less than 90 degrees. What do I mean by that? Okay, I'm just going to call it as follows. If this is my direction of motion, and this is the force applied, and this force applied can be at any angle, then I call the smallest angle between these two. You see there's this angle between these two, and then there's the outside angle. I call the smallest angle, I call the interior angle. Now if the smallest angle between the direction of motion and the and the force, if that angle is less than 90 degrees, then the work done will be positive. But if that value is more than 90 degrees and less than 180, then the work done will be negative. So positive works just tell me that the angle between the force done and the direction which this thing is moving is less than 90 degrees, and negative works tells me that the angle between the direction in which something moves and the force that is applied is more than 90 degrees. Okay, grade 12s. Here is quite a tricky problem. See if you can handle this one. A learner throws a rigid board in such a way that it reaches the top of a 3-meter wall as shown in the sketch. He drags the 5-meter crate with a force of 15 Newton at a constant velocity to the top of the board. First, I want you to calculate the work done by the gravitational force as he drags the crate to the top. And then I would like you to do the work done by the frictional force that is acting on the board. See if you are able to figure out this one. The problem that we have here is that there's no theta. Is there a way that you could figure out how to do this? Maybe if you look at the video on the use of trigonometry in science, this could give you a clue. Good luck.